About 299 million years ago, the Permian Period began, marking one of the most important chapters in Earth's history. It lasted until about 252 million years ago, bringing dramatic changes to the planet's land, climate, oceans, plants, and animals. During this time, nearly all the continents joined together to form one giant landmass, while vast deserts spread across many regions. New groups of reptiles, amphibians, insects, and seed plants appeared and flourished as older forms of life declined. The Permian Period also ended with the greatest mass extinction ever known, an event that destroyed most living species and completely changed the future of life on Earth, shaping the world that followed. The Permian Period began about 299 million years ago and lasted until about 252 million years ago. It was the last period of the Paleozoic era, a very long chapter in Earth's history that came before the age of the dinosaurs. During this time, the planet experienced major changes in its land, seas, climate, plants, and animals. Many living things that had appeared during earlier periods continued to develop, while many new forms of life also emerged. The Permian was a time of both growth and struggle, with living organisms constantly adapting to changing conditions across the world. At the beginning of the Permian Period, the continents of Earth were slowly coming together to form one enormous landmass known as Pangaea. Almost all of the world's land became connected into this single supercontinent. Around Pangaea lay a vast global ocean called Pangaea. There was also a smaller ocean known as the Paleotethys Ocean that stretched along part of the eastern side of the supercontinent. The joining of the continents changed the movement of winds, rainfall, ocean currents, and temperatures. These changes affected every living thing on land and in the sea. The center of Pangaea was located far from the oceans. Because of this, large parts of the land became dry and received very little rainfall. Many regions developed deserts, dry plains, rocky areas, and seasonal rivers that only carried water during certain times of the year. Some places still had forests, rivers, lakes, and wetlands, but many areas became much drier than they had been during earlier periods. Living things had to adjust to these new conditions if they were to survive. The climate during the Permian Period was very different from place to place. Areas close to the coast often had more moisture, while the middle of the supercontinent experienced hot summers, cold winters, and long dry seasons. Some southern regions remained cooler because they were closer to the South Pole. At the beginning of the Permian, large ice sheets still covered parts of the southern continents. Over time, these glaciers slowly melted as the climate became warmer across much of the world. This warming affected sea levels, weather patterns, and the environments where plants and animals lived. The atmosphere also continued to change during the Permian Period. Oxygen levels were different from those of today, and the amount of carbon dioxide in the air changed over time because of volcanic activity, plant growth, and natural processes inside the Earth. These changes influenced temperatures and affected how living things breathed and grew. Scientists study rocks, fossil plants, ancient soils, and tiny bubbles trapped in minerals to understand the atmosphere of this distant time. The land itself was constantly changing. Powerful forces inside the Earth pushed pieces of the crust together, creating mountain ranges in different parts of the supercontinent. Old mountains continued to wear down through erosion caused by wind, rain, rivers, and ice. Rivers carried sand, mud, and gravel into valleys, lakes, and shallow seas where these materials slowly formed layers of sediment. Over millions of years, these sediments turned into rock, preserving evidence of ancient environments. The Permian landscape included deserts covered with sand dunes, rocky hills, wide river valleys, forests of tall plants, freshwater lakes, marshes, and coastal regions where the land met the sea. Each environment supported different kinds of living organisms. Plants and animals became suited to the places where they lived. Those living in dry regions developed different features from those living in wetter forests or shallow seas. Plant life continued to evolve throughout the Permian period. Earlier forests dominated by giant club mosses, horsetails and seed ferns gradually changed. As the climate became drier, many of these older plants became less common in dry regions because they depended on large amounts of water for reproduction and growth. New groups of seed plants became more successful because they could survive with less water. Their seeds protected young plants during dry conditions and allowed them to spread into many different environments. Conifers became some of the most important plants of the Permian. They had strong woody trunks, narrow leaves, and seeds that helped them survive in dry climates. Their leaves reduced the amount of water lost to the air, making them well suited for regions with little rainfall. Other seed-bearing plants also spread across the land, forming forests in areas where conditions allowed them to grow. The spread of seed plants affected many other living things. Animals found food, shelter, and places to reproduce among these plants. Dead leaves, branches, and roots became food for fungi and tiny organisms that broke down organic material. This process returned nutrients to the soil, helping new plants grow. The relationships between plants, fungi, insects, and animals became increasingly complex. Insects remained among the most successful groups of animals during the Permian period. Many kinds of insects filled forests, grass-like vegetation, wetlands, and dry regions. Some fed on leaves, wood, seeds, or dead plant material. Others hunted smaller insects. Different mouth parts allowed insects to eat different kinds of food. Some developed wings that helped them travel longer distances in search of food or suitable places to lay eggs. The Permian period also witnessed major developments among vertebrate animals. Fish continued to live in rivers, lakes, and oceans. Sharks remained important predators in marine environments. Bony fish became more diverse and occupied many different habitats. Freshwater ecosystems supported many species that hunted insects, smaller fish, and other aquatic animals. Amphibians still lived in many freshwater environments. They were especially common around rivers, lakes, ponds, and wetlands where they could reproduce in water. Some amphibians grew to large sizes and hunted fish or smaller land animals. However, the increasingly dry climate made life more difficult for many amphibian groups because their eggs usually required water to develop. Reptiles became much more successful during the Permian because they possessed important features that helped them live away from water. Their skin reduced water loss, and their eggs contained protective coverings that allowed young animals to develop on land without depending on ponds or lakes. These adaptations allowed reptiles to spread across deserts, forests, and open plains. Among the reptiles were many different groups that looked very different from one another. Some were small insect eaters, while others became plant eaters or meat eaters. Their bodies, teeth, jaws, and limbs gradually changed as they adapted to different environments and food sources. Evolution continued to produce many forms of life, each suited to particular conditions. One important group during the Permian included the synapsids. These animals are often called mammal-like reptiles, although scientists now understand that they belong to their own branch of vertebrate evolution that eventually gave rise to mammals. Synapsids became some of the dominant land animals of the Permian. They displayed a wide variety of body shapes and lifestyles. Some synapsids fed mainly on plants. They had broad bodies, strong legs, and teeth suited for cutting and grinding vegetation. Others became active hunters with sharp teeth designed for catching prey. Their skeletons show evidence of increasingly powerful jaws and improved movement. Some may even have had features related to better control of body temperature. Although scientists continue to study these possibilities, one of the well-known plant-eating synapsids was Dimetrodon, which actually lived during the earlier part of the Permian. It possessed a large sail supported by long bones extending from its back. Scientists continue to study the purpose of this structure. Some believe it may have helped control body temperature, while others suggest it may have been used for display or recognizing members of the same species. Another important group included therapsids, which appeared later in the Permian. These animals developed several features that later became common among mammals. Their jaws, teeth, limbs, and posture gradually changed over time. Different therapsids filled many ecological roles, including hunters, plant-eaters, and animals that fed on a variety of foods. Life in the oceans remained rich and diverse throughout much of the Permian Period. Coral reefs supported many kinds of marine organisms. Sponges, brachiopods, mollusks, sea lilies, sea stars, trilobites, ammonoids, and many other animals lived in shallow seas. Larger predators hunted smaller creatures while countless tiny organisms floated in the water and formed the base of marine food chains. Many shell-bearing animals built hard coverings that protected them from predators. When these animals died, their shells often settled onto the sea floor and became buried under layers of sediment. Over millions of years, these remains became fossils. Today, paleontologists use these fossils to understand ancient marine environments and how different species evolved. The Permian oceans contained many different habitats. Shallow coastal waters supported rich communities of life because sunlight reached the sea floor, allowing plants and algae to grow. Deeper waters contained different organisms adapted to darker conditions. Ocean currents carried nutrients across the seas, supporting countless living things. Volcanic activity continued during the Permian Period. Volcanoes erupted in different regions, releasing lava, ash, gases, and other materials into the environment. Most volcanic activity was part of Earth's normal geological processes. However, toward the end of the Permian, enormous volcanic eruptions occurred in what is now northern Asia. These eruptions covered huge areas with lava and released massive amounts of gases into the atmosphere. These volcanic events affected Earth's climate in many ways. Gases released into the air influenced temperatures and weather patterns. Ash and dust spread through the atmosphere. Oceans also changed as increasing amounts of carbon dioxide entered the water. Scientists continue to study exactly how these events influence the environment and living organisms. Throughout the Permian, life continued adapting to changing conditions. Natural selection favored organisms with features that improved survival and reproduction. Plants better able to conserve water spread across dry landscapes. Animals with stronger limbs moved more effectively across land. Teeth evolved into different shapes for eating plants, insects, meat, or mixed diets. These gradual changes occurred over millions of years. Predator and prey relationships also became more complex. Hunters developed improved senses, stronger jaws, faster movement, and better methods for catching food. Plant eaters developed defenses such as thicker skin, larger bodies, protective structures, or behaviors that reduced the risk of attack. These interactions influenced the evolution of many groups. The soils of the Permian varied greatly depending on climate and location. dry regions often had sandy or rocky soils with limited plant growth. Wetter regions supported richer soils where forests developed. Rivers carried nutrients from mountains into valleys. Wetter regions supported richer soils where forests developed. Rivers carried nutrients from mountains into valleys, helping vegetation grow in suitable locations. Ancient soils preserved in rocks provide important clues about rainfall, temperature, and plant life. Seasonal changes became important across much of Pangaea. Some areas experienced long dry seasons, followed by periods of rainfall. Rivers expanded during wet seasons and shrank during dry times. Animals often had to travel in search of water and food. Plants developed life cycles suited to changing seasons, producing seeds capable of surviving difficult conditions. Fire likely played an important role in some Permian ecosystems. Lightning could ignite dry vegetation, leading to natural wildfires. Plants and animals living in these environments gradually adapted to occasional fires. Charcoal preserved in ancient rocks provides evidence that fires occurred during parts of the Permian. The fossil record of the Permian comes from many parts of the world. Fossils have been discovered in North America, South America, Europe, Asia, Africa, Antarctica, and Australia. These discoveries include bones, teeth, shells, footprints, burrows, leaves, seeds, pollen, wood, and microscopic organisms. Each fossil helps scientists understand the lives of organisms that lived millions of years ago. Footprints preserved in ancient mud reveal how some animals walked, ran, or rested. Burrows show that many animals dug into the ground for protection from heat, cold, or predators. Fossilized droppings contain remains of food, helping scientists learn what ancient animals ate. Even tiny grains of fossil pollen provide valuable information about ancient forests and climate. The formation of the supercontinent Pangaea was one of the most important events in the long history of Earth. It was not something that happened in a short time. It took many millions of years as the great landmasses slowly moved across the surface of the planet. During this long period, continents that had once been separated by wide oceans gradually came closer together until they became connected. This process changed the shape of Earth, the movement of the oceans, the pattern of the atmosphere, the climate, the lives of plants and animals, and the conditions under which rocks, mountains, and minerals formed. Earth has never had a surface that remained the same. The outer layer of the planet is broken into large pieces called tectonic plates. These plates move very slowly over a softer layer beneath them. The movement is usually only a few centimeters each year, but over millions of years, these small movements become very large. Continents rest on these moving plates, so they also move across Earth's surface. This slow movement is known as continental drift, while the broader process, involving the movement of the plates, is called plate tectonics. Long before Pangaea existed, Earth's continents were arranged in many different ways. Smaller pieces of land slowly joined together to form larger continents. At other times, large continents broke apart into smaller pieces. This cycle of joining and separating has happened many times throughout Earth's history. Scientists believe that Pangaea was only one of several supercontinents that formed during different ages of the planet. The formation of Pangaea began long before the Permian Period. During earlier geological periods, many separate continents were already moving towards one another. Oceans between them slowly became narrower as the tectonic plates carried the land closer together. The edges of continents collided after long periods of movement. These collisions created mountain ranges, changed the shape of coastlines, and closed many ancient oceans. One of the largest continents before Pangaea was Gondwana. Gondwana included land that later became South America, Africa, Antarctica, Australia, the Indian subcontinent, and the Arabian Peninsula. These lands were connected for a very long time before they joined with other continents. Gondwana covered a huge area in the southern part of the world and contained many different environments, including forests, rivers, mountains, deserts, lakes, and coastal regions. Another major landmass was Laurussia, sometimes called Euramerica. It was formed when earlier continents joined together. Laurussia included much of what later became North America and large parts of Europe. It was located north of Gondwana. Between these large landmasses lay wide oceans that slowly became smaller, as plate movement continued over millions of years. Another important continent during this time was Siberia. It existed as a separate landmass before joining the growing supercontinent. Other smaller blocks of continental crust also moved across the oceans and became attached to larger landmasses through a series of collisions. The movement of tectonic plates was driven by heat from deep inside Earth. The planet's interior remains extremely hot because of leftover heat from its formation and the natural breakdown of radioactive elements. This heat creates slow-moving currents inside the mantle. These currents help move the tectonic plates above them. Although this movement is too slow to notice during a human lifetime, it becomes very important over millions of years. As continents moved closer together, the ocean floor between them was pushed beneath the edges of the continents through a process called subduction. In these areas, one tectonic plate slid beneath another and descended into the mantle. This caused powerful earthquakes, volcanic eruptions, and the formation of chains of volcanoes. The ocean separating the continents gradually became smaller until the continents finally collided. When continents collided, neither continent easily sank beneath the other because continental crust is lighter than oceanic crust. Instead, the edges were squeezed together. Layers of rock folded, cracked, and were pushed upward. This created long mountain ranges that stretched for great distances. Many ancient mountain systems around the world formed during these continental collisions. One important mountain-building event occurred when the land that became North America collided with Africa and Europe. This collision formed part of the mountain system that included the ancient Appalachian Mountains. At the time they formed, these mountains were much taller than they are today. Millions of years of erosion slowly wore them down to their present height. Another important collision occurred as Gondwana slowly approached Laurussia. The closing ocean between these continents eventually disappeared. When the landmasses met, they became joined into one enormous continent. This marked one of the final stages in the formation of Pangaea. By the late part of the Carboniferous period and into the Permian period, most of Earth's major landmasses had become connected. Pangaea stretched from near the northern polar regions to far into the southern polar regions. It covered an enormous part of Earth's surface and was surrounded by a vast global ocean called Panthalassa. Along one side of Pangaea lay another large body of water known as the Paleo-Tethys Ocean. The size of Pangaea was unlike anything seen on Earth today. Almost all major continental land was connected into one giant landmass. Instead of many separate continents divided by wide oceans, there was one enormous continent with an irregular shape. Long coastlines bordered the surrounding ocean, while vast inland regions lay very far from the sea. The shape of Pangaea had a major effect on climate. Coastal areas received moisture carried by winds from the oceans. Rain fell more often near the coasts, allowing forests and other plant life to grow in many regions. Rivers carried water from mountains toward the sea. Wetlands developed in some places, providing homes for many kinds of plants and animals. the interior of Pangaea experienced very different conditions. Because these regions were located far from the oceans, little moisture reached them. Rainfall became much less common. Many inland areas became dry for long periods. Rivers were fewer, lakes were smaller, and deserts expanded across large parts of the continent. Seasonal weather also became stronger across many parts of Pangaea. During the warm season, inland regions became very hot because land heats more quickly than water. During the cool season, temperatures dropped because there was little nearby ocean water to reduce these changes. This produced large seasonal differences across much of the continent. The formation of Pangaea also affected wind patterns. Air moved differently across such a large landmass than it does across today's separated continents. Winds carried moisture along new paths. Some regions became wetter, while others became drier. Storm systems developed differently because of the changing arrangement of land and sea. Ocean currents also changed as the continents came together. The movement of water around Earth depends greatly on the position of continents. When Pangaea formed, the large surrounding ocean allowed water to flow in new directions. These changing currents affected temperatures in coastal regions and influenced weather across the planet. The joining of continents also changed sea levels in many areas. As mountain ranges rose and ocean basins changed shape, some shallow seas disappeared while others formed. Coastal environments shifted many times. Areas that had once been underwater became dry land, while other regions were flooded by rising seas. The formation of Pangaea affected living organisms in many ways. Plants and animals that had once been separated by oceans were able to spread across connected land. Species moved into new environments where they encountered different climates and other forms of life. Some species successfully expanded their range, while others remained limited to certain regions because of environmental conditions. Large forests spread across many parts of Pangaea where rainfall was sufficient. Different groups of plants grew depending on local climate. Seed plants became especially successful during this time because they could survive under drier conditions than many earlier plants that depended on constant moisture for reproduction. Animals also benefited from connected land. Many reptiles spread into new regions because they were well suited to dry environments. Their eggs contained protective coverings that reduced water loss, allowing them to reproduce away from lakes and rivers. This helped reptiles become increasingly successful across much of Pangaea. Early relatives of mammals also lived during this time. Many belonged to a group known as synapsids. These animals occupied many different habitats across the supercontinent. Some were plant eaters, while others hunted smaller animals. Their widespread distribution was made possible by the connected land. Insects continued to diversify as forests, grass-free woodlands and dry environments expanded across different parts of Pangaea. Many insects adapted to particular plants, while others became hunters or scavengers. Their ability to fly allowed them to spread over wide areas. Freshwater environments, such as rivers and lakes, remained important even though many inland regions became dry. Fish lived in rivers and lakes where water remained available throughout the year. Amphibians were common in wetter areas because they required water for reproduction. Their distribution became more limited in the driest regions. The formation of mountain ranges during continental collisions created many new environments. Higher elevations experienced cooler temperatures than nearby lowlands. Rain often fell on one side of mountains, while the opposite side remained much drier. These differences produced many local habitats where different plants and animals could survive. Erosion became very active after mountains formed. Rain, rivers, wind, ice, and changes in temperature slowly broke down exposed rocks. Small pieces of rock were carried away and deposited in valleys, river plains, lakes, and coastal regions. Over long periods, these sediments formed thick layers that later hardened into sedimentary rocks. Many valuable mineral deposits formed during the processes associated with continental collisions. Heat, pressure, and underground fluids concentrated different minerals within Earth's crust. These geological processes created deposits of metals and other useful materials that people mine today. Volcanic activity accompanied many stages of Pangaea's formation. As oceanic plates sank beneath continents, molten rock rose toward the surface. Volcanoes erupted, releasing lava, ash, gases, and other materials. These eruptions created volcanic mountains and added new rock to Earth's surface. Earthquakes were also common along active plate boundaries. As tectonic plates pushed, pulled, or slid past one another, stress built within rocks. When the rocks finally broke or shifted, earthquakes occurred. Many powerful earthquakes likely happened during the long formation of Pangaea. The atmosphere was also affected by changing landscapes. Mountain building influenced wind movement and rainfall. Expanding forests removed carbon dioxide from the atmosphere through photosynthesis while releasing oxygen. Volcanic eruptions added gases including carbon dioxide and water vapor. These natural processes influenced climate over long periods. Large river systems developed across different parts of Pangaea. Rivers carried water from mountains to lower areas and eventually toward the surrounding ocean. Along the way, they transported enormous amounts of sand, mud, and gravel. Floodplains formed beside many rivers, creating fertile environments where plants flourished. Lakes varied greatly in size depending on climate and geography. Some existed for long periods, while others dried up during extended dry seasons. Salt lakes formed in some inland basins where water evaporated faster than it could flow away. Deserts expanded across broad inland regions because moist air from the oceans could not easily reach these areas. Wind shaped sand into dunes that shifted over time. Dry river channels filled only after occasional heavy rainfall. Plants that survived in these regions developed ways to reduce water loss. Although much of central Pangaea was dry, not every inland area was a desert. Some regions contained rivers fed by distant mountains. Others received seasonal rainfall that supported woodlands and scattered forests. Climate varied greatly depending on local geography, elevation, and wind patterns. The southern part of Pangaea experienced major environmental changes following earlier ice ages. Large ice sheets that had covered parts of Gondwana gradually disappeared as climate changed. The retreat of glaciers left behind valleys, lakes, and deposits of rock and sediment. These features remained as evidence of earlier cold conditions. Scientists have learned about Pangaea through many different kinds of evidence. One important clue comes from the shapes of today's continents. The coastlines of South America and Africa fit together remarkably well when reconstructed. Although modern coastlines have changed through erosion and rising sea levels, the deeper edges of the continental shelves fit even more closely. Fossils provide another important source of evidence. The same species of ancient plants and animals have been found on continents now separated by wide oceans. These organisms could not have crossed such vast bodies of water. Their fossils suggest that the continents were once connected. Ancient rock layers also support the existence of Pangaea. Rocks of the same age and type occur on continents now separated by oceans. Mountain ranges that end at one coastline continue on another continent when the continents are placed back together. These matching geological features provide strong evidence that the landmasses were once joined. scientists also study magnetic minerals preserved within rocks. As molten rock cools, tiny magnetic minerals align with Earth's magnetic field. These minerals preserve information about the position of the rocks at the time they formed. By measuring this ancient magnetism, scientists can determine how continents have moved over millions of years. Modern technology has greatly improved the understanding of continental movement. Satellites measure the present movement of tectonic plates with great accuracy. These measurements show that continents are still moving today, although the movement is extremely slow. The current motion supports the idea that continents have been moving throughout Earth's history. Computer models help scientists reconstruct the formation of Pangaea. Information from fossils, rocks, magnetic records, and plate movements is combined to estimate the positions of continents at different times. These reconstructions continue to improve as new discoveries are made. The formation of Pangaea also influenced the evolution of life by changing migration routes. Animals no longer needed to cross oceans to move between many regions. Land connections allowed populations to spread over great distances. Some groups expanded into areas where they had never lived before. Competition among species changed as new populations met. Different animals and plants occupied similar habitats after the continents joined. Natural selection acted upon these populations over many generations. Some species became widespread across large parts of Pangaea, while others disappeared from certain regions. Changes in rainfall affected the distribution of forests. Wet coastal regions supported dense vegetation, while drier inland areas contained fewer trees. Plant communities adapted to local conditions. Different kinds of seeds, leaves, roots, and stems developed according to available water and temperature. Fire probably became an important natural process in some dry forests and woodlands. Lightning could ignite dry vegetation during certain seasons. Fires cleared old plant material and influenced which plants survived in different environments. Evidence of ancient wildfires has been preserved in some rock layers from this period. Soils also changed across Pangaea. Wet climates produced different soil types from dry climates. Rivers deposited fresh sediment during floods, creating fertile floodplains. Wind carried fine dust across deserts and nearby regions. Chemical weathering altered minerals according to local temperature and rainfall. The coastline of Pangaea extended for many thousands of kilometers around the giant continent. Shallow coastal waters supported many marine organisms, including shellfish, corals, fishes, and many microscopic forms of life. These coastal ecosystems were affected by tides, storms, river sediments, and changing sea levels. Marine life outside the continent also responded to the new arrangement of land and sea. Ocean circulation influenced water temperature, oxygen levels, and nutrient movement. Some marine species spread into new areas, while others became isolated in different parts of the oceans. The long process that formed Pangaea did not stop once the continents became connected. Tectonic plates continued moving beneath the surface. Stress slowly accumulated within the enormous continent. Deep inside Earth, the forces responsible for bringing the continents together continued to operate. These same forces eventually led to the breaking apart of Pangaea many millions of years later, although that process belonged to a later chapter in Earth's geological history. Throughout the time that Pangaea existed, mountains continued to erode, rivers continued to carve valleys, volcanoes continued to erupt, earthquakes continued to reshape the land, and living organisms continued to adapt to changing environments. The supercontinent remained a dynamic part of an active planet whose surface was constantly changing through natural geological processes. The Permian Period began about 299 million years ago and lasted until about 252 million years ago. During this long part of Earth's history, the climate and weather changed in many places across the planet. Some regions remained dry for very long periods, while others received regular rainfall. Some places experienced very hot days, while others had cooler conditions for much of the year. The shape of the continents, the movement of the oceans, the height of mountain ranges, and the position of the land all influenced the climate. These natural conditions created many different environments where plants and animals lived. One of the most important features of the Permian world was the formation of the giant supercontinent called Pangaea. Almost all of Earth's land was connected into one enormous landmass. This changed the movement of air and water around the planet. Since there were fewer large seas reaching deep into the land, much of the interior of Pangaea was located far away from the cooling and moistening effects of the oceans. As a result, many inland areas became dry and experienced very little rainfall throughout the year. The oceans have a strong effect on climate because they store large amounts of heat and release moisture into the air. Coastal areas usually receive more rain because winds carry water vapor from the sea onto the land. During the Permian, many parts of the great continent were hundreds or even thousands of kilometers from the nearest coastline. Moist air could not easily travel such long distances before losing its water through rain. Because of this, large inland regions became deserts or dry plains where rainfall was uncommon. The weather in these dry regions often remained clear for long periods. Clouds formed less often because there was little moisture in the air. Sunny skies allowed the ground to become very hot during the daytime. At night, temperatures often dropped because there were few clouds to trap heat close to the surface. This created large differences between daytime and nighttime temperatures. Living things that survived in these areas had to cope with both heat during the day and cooler conditions after sunset. Rainfall patterns differed greatly from one place to another. Some regions received rain mainly during certain parts of the year, while others remained dry for many years. Seasonal rains supported forests, rivers, lakes, and wetlands. In contrast, dry regions contained only scattered streams that sometimes disappeared completely during long periods without rain. Water became one of the most important factors controlling where plants and animals could survive. Scientists have learned about the Permian climate by studying many different kinds of evidence. Rocks provide valuable information because different types of rock form under different weather conditions. Thick layers of sandstone often suggest ancient deserts where wind carried loose sand across the landscape. Mudstones may show that quiet lakes or rivers once existed. Coal deposits reveal that thick forests and wetlands covered certain areas for long periods. Salt deposits indicate that shallow bodies of water dried up repeatedly under hot and dry conditions. Fossils also provide important evidence about climate. Different kinds of plants grow best under different temperatures and rainfall levels. The remains of ancient forests show where wetter climates once existed. Fossils of desert plants help identify regions that received little rain. Animal fossils also reveal information about climate because different species were adapted to particular environments. By studying where these fossils are found, scientists can build a picture of how climate varied across the Permian world. During the early part of the Permian, some regions were still recovering from the cold conditions that existed near the end of the previous Carboniferous period. Large ice sheets had covered parts of the southern hemisphere. These massive bodies of ice slowly began to melt as the climate became warmer. Evidence of these ancient glaciers remains preserved in rocks that contain scratches made by moving ice and deposits left behind when glaciers melted. As the glaciers disappeared, sea levels changed. When large amounts of water are locked inside ice sheets, sea levels become lower because less water remains in the oceans. As the ice melted during the Permian, more water returned to the seas. Rising sea levels changed coastlines and affected many coastal habitats. Some shallow seas expanded, while others later disappeared because of movements in Earth's crust. The warming climate allowed many regions to develop new ecosystems. Forests spread into areas that had previously been too cold. Plants adapted to warmer conditions became more common. Animals also expanded into new environments as temperatures increased. The gradual warming did not happen at the same speed everywhere. Some areas warmed more quickly, while others changed more slowly depending on their location and geography. The position of the continents also affected global wind patterns. Warm air near the equator rose into the atmosphere, while cooler air moved toward lower latitudes. These movements created large systems of winds that influenced rainfall and temperature. Mountains forced air upward, causing rain to fall on one side while leaving the opposite side much drier. These effects produced different climates even within the same continent. Mountain ranges played an important role in shaping local weather. When moist air moved toward mountains, it rose along the slopes. Rising air cooled, allowing water vapor to condense into clouds and rain. After losing much of its moisture, the air descended on the other side of the mountains, becoming warmer and drier. This created broad, dry regions where very little rain reached the ground. Large deserts expanded across much of the interior of Pangaea. Winds shaped the sandy landscape into dunes that shifted over time. Sandstorms probably occurred when strong winds lifted loose grains into the air. These storms carried dust across great distances. Fine dust settled over wide regions and became part of the soil or accumulated in lakes and rivers. Desert environments supported fewer large plants than wetter regions. Vegetation was usually scattered, with species that could survive long periods without rain. Plants developed thick outer surfaces that reduced water loss. Some produced seeds that remained inactive until enough moisture became available for growth. Deep root systems allowed certain plants to reach water stored beneath the ground. Animals living in these dry environments also developed ways to survive limited water supplies. Many reptiles had skin covered with scales that helped reduce water loss. They produced eggs protected by strong shells, allowing reproduction away from lakes and rivers. These adaptations helped reptiles spread across dry landscapes where amphibians found survival more difficult because they depended more heavily on water for reproduction. The middle part of the Permian was generally warmer than earlier times. Tropical regions experienced high temperatures throughout much of the year. Warm conditions extended into higher latitudes than before. This allowed many kinds of reptiles to spread into new areas. Some large amphibians remained successful near rivers and lakes, but reptiles became increasingly important in many environments. Not every part of the world experienced constant heat. Areas closer to the poles still had cooler climates, especially during winter months. Seasonal changes remained important in these regions. Plants and animals had to survive periods of lower temperatures before warmer weather returned. Evidence from tree growth rings suggests that some forests experienced regular seasonal cycles. Seasonal weather influenced the growth of plants. During wetter seasons, vegetation grew rapidly, producing leaves, seeds, and wood. During dry seasons, growth slowed or stopped until rainfall returned. This seasonal cycle affected animals because the availability of food changed throughout the year. Plant-eating animals often moved in search of fresh vegetation, while meat-eating animals followed the movements of their prey. Large rivers crossed parts of the Permian landscape. Their flow depended on rainfall within distant mountain regions and upland areas. During wet seasons, rivers became larger and sometimes overflowed their banks, leaving layers of mud across nearby floodplains. During dry seasons, water levels fell, exposing wide riverbanks and isolated pools where aquatic animals gathered. Lakes also changed with the seasons. Some lakes remained full throughout the year because they received steady supplies of water from rivers or underground springs. Others expanded during rainy periods and shrank during dry periods. In very hot climates, shallow lakes sometimes dried completely, leaving behind thick layers of minerals as the remaining water evaporated. The oceans influenced global temperatures by moving warm and cool water around the planet. Ocean currents transported heat between different regions, affecting coastal climates. Changes in the arrangement of continents altered these currents during the Permian. Because the continents formed one large landmass, ocean circulation differed greatly from modern patterns, influencing weather around the world. Scientists believe that atmospheric conditions also changed during the Permian. Levels of gases such as carbon dioxide varied over time because of volcanic activity, weathering of rocks, and the growth of forests. These changes influenced global temperatures. Higher amounts of carbon dioxide generally supported warmer climates, while lower amounts allowed cooler conditions to develop. Natural processes operating over millions of years caused these long-term changes. Volcanic eruptions occasionally affected the weather by releasing ash and gases into the atmosphere. Large eruptions could temporarily reduce sunlight reaching the ground because ash blocked part of the incoming solar radiation. Over longer periods, volcanic gases contributed to changes in atmospheric composition. The overall effects depended on the size, frequency, and location of the eruptions. The Permian climate was not completely stable. Long periods of gradual change were interrupted by shorter episodes of unusual weather. Some years may have brought greater rainfall than usual, while others experienced severe drought. These natural variations affected rivers, forests, and animal populations. Species that could tolerate changing conditions often survived more successfully than those that depended upon very specific environments. Evidence from fossil soils shows that many parts of the Permian experienced repeated cycles of wet and dry conditions. These ancient soils preserve features such as cracks formed when the ground dried after periods of rainfall. Mineral deposits inside the soil reveal how water moved through the ground before evaporating. These details help scientists understand the seasonal climate of ancient landscapes. Throughout the Permian, climate remained one of the strongest forces shaping life on Earth. Every plant, animal, river, forest, desert, and coastline was influenced by changing temperatures, rainfall, winds, and seasonal weather. The conditions varied across different regions, creating a wide range of habitats that supported many different forms of life. The variety of climates across the Permian world allowed many different ecosystems to exist at the same time. Dense forests continued to grow in places where rainfall remained dependable and temperatures stayed suitable for plant growth. These forests contained seed ferns, conifers, ginkgophytes, cycads, horsetails, club mosses, and many other kinds of plants. Their leaves captured sunlight and used it to produce food through photosynthesis. Rainfall supplied the water needed for this process, while the warm climate supported continuous growth during favorable seasons. In areas where the weather became dry for several months each year, many plants slowed their growth until moisture returned. Conifer forests became especially important during the Permian, because these trees were well suited to dry conditions. Their narrow leaves reduced the amount of water lost to the air. Thick bark protected the trunks from heat and damage caused by dry weather. Their seeds developed inside protective coverings instead of depending on standing water for reproduction. These features allowed conifers to spread across large regions that had become too dry for many older kinds of plants. The weather strongly influenced the condition of the soil. Frequent rainfall washed minerals through the ground, creating deep and fertile soils in wetter regions. Dry climates slowed this process. In deserts, strong winds often removed fine particles from the surface, leaving behind coarse sand and small stones. In places where rain came only occasionally, water rushed quickly across the land instead of soaking deeply into the soil. This sometimes caused sudden flooding that carried large amounts of sediment into rivers and lakes. Floods were an important part of the Permian environment. Heavy rain falling over mountain regions could cause rivers to rise rapidly. Water spread across nearby plains, carrying mud, sand, plant material, and broken rocks. When the floodwaters slowly moved away, they left behind fresh layers of sediment. Over millions of years, these layers became sedimentary rocks that preserve fossils of plants and animals living during the Permian. Strong winds shaped many parts of the landscape. Dry ground with little vegetation allowed loose sand and dust to be carried easily through the air. Wind gradually built large dunes that changed shape as storms passed over them. Some dunes stretched across wide desert regions. The patterns preserved inside ancient sandstone show how these dunes formed and moved under the influence of steady winds. Dust carried by the wind sometimes travelled very long distances before settling back to the ground. This dust entered rivers, lakes, and shallow seas. It mixed with other sediments and became part of the rock record. Scientists study these deposits to learn about ancient wind directions and the strength of storms that occurred during the Permian. Clouds formed whenever moist air cooled enough for water vapor to condense into tiny droplets. In wetter regions, clouds appeared often and brought regular rainfall. In dry inland areas, clouds were less common because little moisture was available. Many days passed with bright sunshine and clear skies. The lack of cloud cover allowed sunlight to heat the ground strongly during the day. Nighttime weather in dry regions often became much cooler than daytime conditions. Without thick clouds to trap heat close to the surface, warmth escaped into the atmosphere after sunset. Animals living in deserts experienced these daily temperature changes throughout the year. Some became active during cooler hours to avoid the hottest part of the day. Others sheltered inside burrows where temperatures remained more stable. Burrowing became an important way for many animals to survive difficult weather. Underground tunnels protected them from heat, cold, wind, and drought. The soil beneath the surface usually stayed cooler during the day and warmer at night than the open air. Some reptiles, amphibians, insects, and small relatives of mammals likely spent part of their lives inside these shelters. Fossil burrows discovered in Permian rocks provide evidence of this behavior. The amount of rainfall affected freshwater habitats across the continents. Streams that flowed throughout the year supported fish, amphibians, and many kinds of aquatic invertebrates. During periods of drought, smaller streams sometimes dried completely. Fish became trapped inside shrinking pools. Amphibians faced increasing difficulty because they depended upon water for reproduction and early development. These changing conditions influenced where different species could survive. Wetlands remained important in some regions despite the spread of drier climates. Marshes, swamps, and shallow lakes supported thick plant growth. Fallen leaves and branches accumulated in waterlogged ground, where decomposition occurred slowly. Over millions of years, this organic material became coal. Coal deposits found in rocks from the Permian show that moist environments continued to exist even while deserts expanded elsewhere. The weather also influenced the spread of wildfires. During long dry seasons, dead plants became dry enough to burn if lightning struck the ground. Natural fires cleared vegetation from some areas. New plants later grew in the open spaces after rain returned. Charcoal preserved in Permian rocks provides evidence that wildfires occurred during this period. Fire became another natural factor, shaping forests and grass-like plant communities. Lightning storms developed when warm, moist air rose into the atmosphere and formed large clouds. Electrical charges built up inside these clouds until lightning was released. Rain often followed these storms, although some lightning struck dry ground without producing much rainfall. These dry lightning events increased the possibility of natural fires, especially during hot weather. The movement of air around the planet created belts of different climates. Areas close to the equator generally remained warm throughout the year. Some equatorial regions received regular rainfall, while others became seasonally dry depending on local geography and wind patterns. Farther from the equator, temperatures became lower and seasonal changes became stronger. Near the poles, winters remained much cooler than summers, even though the overall climate was warmer than during earlier ice ages. The length of the seasons affected weather patterns. During warmer months, stronger sunlight heated the land more intensely. Warm air rose and influenced the movement of winds over large areas. During cooler months, reduced sunlight lowered temperatures and changed atmospheric circulation. These seasonal shifts altered rainfall, humidity, and cloud formation across many regions. Humidity refers to the amount of water vapor present in the air. Humid conditions developed near oceans, lakes, rivers, and forests where evaporation added moisture to the atmosphere. Dry deserts contained much lower humidity because little water was available to evaporate. Humidity affected how quickly water left the soil and plants. High humidity reduced evaporation, while low humidity allowed water to disappear more rapidly. Evaporation played a major role in the Permian water cycle. Heat from the sun caused water from oceans, lakes, rivers, and wet soil to change into water vapor. This invisible vapor rose into the atmosphere where it cooled and eventually formed clouds. Rain returned the water to Earth's surface, allowing the cycle to continue. The balance between evaporation and rainfall determined whether a region became wetter or drier. Many rivers carried large amounts of dissolved minerals. As water flowed across rocks, it slowly dissolved small quantities of different substances. These minerals were transported downstream into lakes and seas. During periods of strong evaporation, water disappeared while the minerals remained behind. Thick deposits of salt, gypsum, and other evaporite minerals formed in some shallow basins. These deposits provide clear evidence that hot and dry climates existed across parts of the Permian world. Some inland basins had no rivers flowing out of them. Water entered these basins during rainy periods, but could leave only through evaporation. As more water evaporated, dissolved minerals became increasingly concentrated until they formed crystals. Repeated cycles of flooding and evaporation produced thick layers of mineral deposits that remain preserved today. Weather conditions also affected erosion. Rain falling onto exposed rocks gradually broke them into smaller pieces. Flowing rivers carried these fragments away. Wind removed loose sand and dust from dry landscapes. Ice continued to shape a few southern regions during the early Permian, where glaciers still survived. Together, these natural processes slowly changed the shape of mountains, valleys, and plains throughout millions of years. The weather influenced the availability of food for animals. Plant-eating species depended upon healthy vegetation, supported by suitable rainfall and temperatures. During droughts, fewer leaves, seeds, and stems were available. Herbivores sometimes gathered around rivers and lakes where plants continued growing. Meat-eating animals often followed these concentrations of prey because food became easier to find near dependable water sources. The climate also influenced reproduction. Many plants released pollen during particular seasons when weather conditions favored successful fertilization. Seeds matured before dry periods began, so young plants could grow when rain returned. Animals often timed reproduction to match periods when food and water were most abundant. Young animals had better chances of survival if they hatched or were born during favorable weather. Fossil tree rings reveal that many Permian forests experienced changing seasonal conditions. Trees usually formed wider rings during years with good rainfall and narrower rings during drier years. By studying these patterns, scientists learn about long-term changes in rainfall and climate. Some fossil trees show many years of steady growth, while others record repeated periods of drought. Large volcanic regions occasionally released huge amounts of gases into the atmosphere over extended periods. Carbon dioxide entered the air from these eruptions and influenced Earth's climate. Sulfur-rich gases also affected the atmosphere for shorter periods. Ash settled across the land and into the oceans. The effects varied depending on the size of each eruption and the length of volcanic activity. Toward the later part of the Permian, volcanic activity became especially important in shaping global climate. Massive eruptions released enormous amounts of lava, along with large quantities of gases, into the atmosphere. These events affected temperatures, rainfall patterns, ocean chemistry, and the balance of gases in the air. Many scientists believe these environmental changes became increasingly severe during the closing stages of the Permian. Changes in ocean temperatures influenced marine weather as well. Warmer surface waters increased evaporation, adding more moisture to the atmosphere above the oceans. Changes in ocean circulation affected how heat moved between different parts of the world. Coastal climates responded to these changes, sometimes becoming warmer, cooler, wetter, or drier over long periods. The atmosphere of the Permian continued to evolve because of interactions among volcanoes, forests, oceans, rocks, and living organisms. Plants removed carbon dioxide from the air during photosynthesis and released oxygen. Animals used oxygen for respiration and returned carbon dioxide to the atmosphere. Volcanoes added new gases, while weathering of rocks removed some carbon dioxide over long periods. These continuous natural processes helped shape the climate throughout the Permian Period. The weather never remained exactly the same from one year to the next. Wet years, dry years, hot summers, cooler seasons, storms, floods, droughts, and changing winds formed part of the natural pattern of the Permian world. Every region experienced its own local combination of temperature, rainfall, humidity, wind, and seasonal change, creating the wide variety of environments that supported the many forms of life living across the supercontinent and the surrounding seas. One of the most important parts of the Permian world was its vast system of oceans, seas, and coastlines. Water covered a large part of Earth, although the amount of land was greater than during many other periods, because most of the continents had joined together into one enormous landmass known as Pangaea. The arrangement of the oceans and the shape of the coastlines affected almost every part of life on Earth. They influenced climate, rainfall, ocean currents, marine life, the movement of sediments, and the places where plants and animals could survive. The largest body of water during the Permian was the great global ocean called Pangaea. This huge ocean surrounded the giant continent of Pangaea on nearly every side. Pangaea stretched across most of the planet and covered an enormous area. Since almost all of the land was joined together, the open ocean formed one vast body of water that connected many different marine environments. Its waters ranged from shallow coastal areas to deep ocean basins. Conditions in these places could be very different depending on their location, water depth, temperature, and distance from land. Pangaea was not a calm and unchanging body of water. Winds blowing across its surface created waves and ocean currents that carried heat, nutrients, and living organisms from one place to another. These currents helped shape weather patterns and affected temperatures across different parts of the world. Some currents carried warm water away from tropical regions, while others moved cooler water from higher latitudes toward lower latitudes. The movement of water helped spread marine life and carried tiny floating organisms over great distances. Although Pangaea was the largest ocean, it was not the only important body of water during the Permian. Another major ocean was called the Paleotethys Ocean. This ocean lay between different parts of the giant continent and connected many shallow seas. The Paleotethys Ocean contained warm waters that supported rich communities of marine life. Many groups of animals lived along its shores and within its shallow waters because sunlight reached the sea floor, allowing algae and other simple organisms to grow in large amounts. The shape of the Paleotethys Ocean changed slowly throughout the Permian because Earth's crust was always moving. Huge pieces of the crust, known as tectonic plates, continued to shift even though the continents had come together. These slow movements changed the positions of coastlines, created new shallow seas and closed older marine passages. These changes happened so slowly that no living creature could notice them during its lifetime, but over millions of years they completely changed the appearance of the planet. Large parts of the Permian coastline stretched for thousands of kilometers around Pangaea. These coastlines were not all alike. Some were steep and rocky, while others were flat and sandy. Many places had broad coastal plains where rivers flowed into the sea. These rivers carried sand, mud, clay, and small stones from the interior of the continent. As the rivers reached the ocean, they slowed down and dropped these materials along the shore. Layer after layer of sediment built up over long periods and formed thick deposits that later hardened into sedimentary rocks. Many Permian coastlines experienced regular changes in sea level. At certain times, the sea advanced farther onto the land, covering large areas with shallow water. At other times, the sea moved back towards deeper parts of the ocean, exposing land that had previously been underwater. These repeated changes created alternating layers of marine and land sediments. Today, geologists study these rock layers to understand how coastlines shifted throughout the Permian. Shallow seas covered many low-lying regions during different parts of the Permian. These shallow waters were often warm because sunlight easily reached the sea floor. Warm temperatures supported many forms of life, including sponges, corals, shellfish, sea lilies, brachiopods, bryozoans, mollusks, echinoderms, ammonoids, and many kinds of fish. The seafloor contained soft mud in some places and clean sand in others. Different animals preferred different environments, depending on the amount of sunlight, oxygen, food, and water movement. Many shallow marine environments contained reefs. These Permian reefs were built by different groups of living organisms, than the reefs seen in today's oceans. Sponges played a very important role in building many reefs. Various algae also helped create strong reef structures by trapping sediments and producing hard materials that became part of the reef. These reefs formed barriers that protected quieter waters behind them. Many smaller marine animals found shelter inside the spaces within the reef. Life around these reefs was rich and varied. Small fish swam among the reef structures, while larger fish searched for food nearby. Shell-bearing animals attached themselves to hard surfaces. Tiny floating organisms drifted through the water and became food for many larger animals. Predators hunted prey among the rocky openings, while scavengers fed on dead material that settled onto the seafloor. Every part of the reef supported different forms of life that depended on one another. Some parts of the Permian Ocean were much deeper. Sunlight could not reach the deepest waters, making conditions very different from those in shallow seas. The deep ocean floor received a slow rain of dead organisms, fine mud, volcanic ash, and other materials falling from the waters above. Over long periods, these materials formed thick layers of sediment. Deep water environments usually contained fewer large animals than shallow coastal regions because food was less abundant. The chemistry of ocean water changed from place to place. In shallow tropical seas, warm temperatures caused water to evaporate quickly. As water disappeared into the atmosphere, dissolved minerals became more concentrated. Eventually, these minerals formed thick deposits of salt, gypsum, and other evaporate rocks. Many of these deposits still exist today and provide valuable evidence about the dry climates that affected parts of the Permian world. Some inland seas became partly separated from the open ocean. Water entered these basins through narrow channels, but did not always flow out easily. During hot and dry periods, evaporation removed large amounts of water while leaving dissolved salts behind. As evaporation continued, salt crystals settled to the bottom and slowly formed thick layers. These deposits could become hundreds of meters thick after very long periods. Not all Permian coastlines were warm. Some regions closer to the southern polar areas experienced much colder conditions, especially during the early part of the period. Ice sheets still existed across parts of the southern continent. Cold coastal waters supported different kinds of marine life than those living in tropical regions. As the climate gradually became warmer, through much of the Permian, many glaciers melted and sea levels changed. These changes influenced coastlines across many parts of the world. The shape of Pangaea had a strong influence on its coastlines. Since nearly all land was connected, the total length of coastline was smaller than if the continents had been spread apart. This meant that many places were located far from the sea. Inland regions often experienced dry conditions because moist air from the oceans could not easily reach them. Coastal regions usually received more rainfall and supported richer plant life than the dry interior. Many large rivers crossed the surface of Pangaea before emptying into the oceans and seas. These rivers formed wide valleys and carried huge amounts of sediment. River mouths created deltas where channels split into many smaller branches before reaching the sea. These deltas supported a wide variety of plants and animals. Mud collected in quiet waters, while sand accumulated where waves and currents were stronger. Estuaries formed where rivers met the sea. In these places, fresh water mixed with salty ocean water. The mixture created unique conditions that supported organisms able to live in changing levels of salt. Fine sediments settled in calm estuaries, providing soft bottoms where many animals burrowed into the mud for protection and food. Tides affected many Permian coastlines. The pull of the moon caused sea levels to rise and fall every day, just as it does today. During high tide, seawater spread farther inland across beaches and tidal flats. During low tide, these areas became exposed to the air. Many marine animals adapted to these regular changes by hiding beneath the sand or attaching themselves firmly to rocks. Wave action constantly reshaped coastlines. Strong waves broke against rocky shores, wearing away cliffs and carrying broken rock fragments into the sea. On sandy shores, waves moved grains of sand back and forth, creating beaches that slowly changed shape over time. Storms sometimes caused sudden erosion, washing away parts of the coast and depositing sediment elsewhere. Powerful storms occasionally crossed the Permian oceans. Strong winds produced large waves that battered coastlines and disturbed shallow marine environments. Storms stirred up sediments from the seafloor and spread them across wide areas. Many marine organisms were buried during these events, and their remains sometimes became fossils, preserved within storm deposits. Ocean currents helped distribute oxygen through many parts of the sea. Surface waters mixed with deeper waters in some regions, bringing fresh oxygen downward and carrying nutrients upward. This circulation supported marine ecosystems by providing the conditions needed for many organisms to survive. However, some deeper basins received very little oxygen because water circulation was weak. Animals living there had to survive under difficult conditions, and some places could support only limited forms of life. Microscopic organisms played an essential role in Permian oceans. Tiny algae floated near the surface where sunlight allowed them to produce food through photosynthesis. These organisms formed the base of marine food chains. Small animals fed on the algae, medium-sized animals fed on the smaller ones, and larger predators hunted them all. When microscopic organisms died, many sank to the seafloor and became part of marine sediments. Many kinds of plankton drifted with ocean currents instead of swimming against them. Some had tiny shells made of calcium carbonate or silica. After death, these shells settled to the bottom and gradually formed thick deposits. Over millions of years, these deposits became sedimentary rocks that scientists study to understand ancient marine environments. Brachiopods were among the most common shell-bearing animals in Permian seas. They lived on the sea floor and filtered tiny food particles from the water. Many attached themselves to rocks or rested on soft mud. Different species occupied different depths and water conditions, making them useful for studying ancient marine environments. Ammonoids were another important group of marine animals. They possessed coiled shells divided into many chambers. These active swimmers moved through open waters in search of food. Their shells varied greatly in size and shape. Since ammonoids evolved rapidly through time, their fossils helped scientists determine the ages of rock layers from different parts of the world. Many fish lived throughout the Permian oceans. Some had skeletons made mainly of bone, while others belonged to the group that includes sharks. Different species occupied reefs, shallow coastal waters, open oceans, and deeper marine environments. Some hunted smaller fish, while others fed on shellfish, worms, or tiny floating organisms. Sharks were already successful predators during the Permian. Many forms looked different from modern sharks, although they shared several important features. They possessed rows of sharp teeth that were continuously replaced throughout life. Different species had different feeding habits depending on the kinds of prey available in their habitats. The sea floor supported countless small creatures that burrowed through mud and sand. Worms dug tunnels beneath the surface, while shell-bearing animals searched for food. These activities mixed sediments together, allowing oxygen to enter deeper layers of the sea floor. Scientists can still find fossil burrows preserved within Permian rocks. Corals lived in warm, shallow seas during the Permian. although many belong to groups that later disappeared. Coral colonies provided homes for many other marine organisms. Different coral species preferred different water depths and temperatures. Healthy coral communities usually required clear water with plenty of sunlight. Sea lilies attached themselves to the sea floor by long stalks. Their feather-like arms captured tiny food particles carried by ocean currents. Large groups of sea lilies sometimes covered extensive areas of the sea floor. When they died, their hard skeletons broke apart and contributed to thick limestone deposits. Bryozoans formed colonies made up of many tiny animals living together. These colonies often covered rocks, shells, or reef surfaces. Their skeletons added to the growing mass of reef structures and provided hiding places for many smaller creatures. The chemistry of seawater influenced which minerals formed in marine sediments. Calcium carbonate was one of the most important substances because many marine organisms used it to build shells and skeletons. After these organisms died, their remains accumulated on the sea floor and eventually formed limestone. Some coastal lagoons became isolated from the open sea. Water trapped inside these basins often became warmer and saltier than surrounding ocean water. Different organisms adapted to these unusual conditions, while others could not survive there. Sediments deposited within lagoons often preserved delicate fossils, because the quiet waters disturbed them very little. Mangrove forests like those of today did not exist during the Permian, but many other plants grew along riverbanks, floodplains, and coastal wetlands. These plants helped hold soil in place and slowed erosion. Fallen leaves, branches, and trunks entered rivers and eventually reached the sea, where some became buried in sediments. Large amounts of organic material accumulated in some coastal swamps. Over long periods, this plant material became buried beneath layers of mud and sand. Pressure and heat slowly changed it into coal in certain regions. Many coal deposits that formed before the Permian continued to influence landscapes during this period, while new deposits formed where suitable conditions existed. Volcanic activity affected some coastlines. Lava flows occasionally reached the sea, creating new coastal land. Volcanic ash fell into both marine and freshwater environments. Ash layers became buried within sediments and now help scientists identify important events in Earth's history, because volcanic materials can often be dated accurately. Earthquakes sometimes changed the shape of coastlines. Sudden movements of Earth's crust could raise parts of the land or lower others beneath the sea. These events altered river courses, created new bays, and changed shallow marine habitats. Although individual earthquakes lasted only a short time, their effects could remain visible for very long periods. Marine sediments from the Permian now appear as rock formations on every continent. Many regions that are dry land today were once covered by shallow seas. Fossils preserved in these rocks reveal the wide variety of life that once filled ancient oceans. Layers of sandstone, limestone, shale, and evaporite rocks each provide different clues about the conditions under which they formed. Scientists study ripple marks preserved in Permian rocks to understand ancient coastlines. These small patterns formed when waves or currents moved sand across the sea floor. Different ripple shapes indicate whether water was shallow or deep, calm or energetic. Mud cracks preserved in coastal sediments show that some areas were exposed to the air before being flooded again. Footprints are sometimes preserved near ancient coastlines where animals walked across wet mud. If the tracks were quickly buried by fresh sediment, they remained protected and eventually turned into fossils. These footprints provide information about the animals that visited beaches, riverbanks, and coastal plains. The color of Permian sedimentary rocks often reflects the environment in which they formed. Red rocks usually formed under dry conditions, where iron minerals reacted with oxygen. Grey and black rocks often formed in environments with little oxygen, where organic matter was preserved more easily. White layers commonly indicate deposits of salt or gypsum formed through evaporation. Some coastlines contained broad tidal flats that stretched for many kilometers. During high tide, these flats lay beneath shallow water. During low tide, they became exposed, leaving behind pools filled with trapped marine organisms. Fine mud settled across these flats, creating smooth surfaces that preserved tracks, burrows, and ripple marks. Barrier islands may have existed along some Permian coasts. These long strips of sand protected quieter waters behind them from the force of large ocean waves. Sheltered lagoons formed between the islands and the mainland, providing habitats for many different marine organisms. The interaction between rivers and the sea constantly reshaped coastal landscapes. Floods delivered fresh sediments while waves and tides spread these materials along the shoreline. Wind also carried sand across beaches, creating dunes near some coasts. These dunes shifted slowly as winds changed direction over time. The position of the continents influenced ocean circulation. Since Pangaea blocked many possible pathways for water movement, currents followed different routes than those of the modern world. These circulation patterns affected temperatures, rainfall, nutrient distribution, and marine ecosystems across the globe. The southern oceans experienced seasonal changes related to the position of the polar regions. Cold water formed near the poles and slowly spread toward lower latitudes. This movement helped transport oxygen into deeper parts of the ocean and influenced marine life far from the polar areas. Many marine animals reproduced by releasing eggs and sperm into the water, where fertilization occurred. Ocean currents then carried young organisms across wide areas before they settled into suitable habitats. This process allowed some species to spread over great distances and occupy many different coastlines. Predators and prey formed complex food networks throughout Permian seas. Small organisms fed on algae. Larger animals hunted the smaller ones. Dead plants and animals became food for scavengers and decomposers. Nutrients released through decomposition returned to the water, supporting new growth of microscopic life. Some marine animals developed thick shells for protection against predators. Others relied on speed, camouflage, burrowing, or hiding among reefs. Different survival strategies allowed many species to share the same environments without using exactly the same food or living space. During different parts of the Permian, regional climates influenced nearby oceans. Dry climates increased evaporation and salt production. Wetter climates supplied greater amounts of fresh water and sediment through rivers. These differences produced a wide variety of marine environments around the edges of Pangaea. The changing level of oxygen in the oceans affected marine ecosystems. Well-oxygenated shallow waters supported abundant life, while poorly oxygenated, deeper basins contained fewer organisms. Periods of reduced oxygen sometimes caused stress for marine communities, leading to changes in which species were most successful. Chemical elements dissolved in seawater came from many sources. Rivers carried minerals weathered from rocks on land. Underwater volcanic activity released additional substances into the ocean. The remains of marine organisms also contributed minerals after death. Together, these sources maintained the chemistry of Permian seawater. As sediments accumulated along coastlines and the seafloor, they recorded countless details about ancient environments. Every layer preserved information about water depth, wave energy, climate, living organisms, and geological activity. By studying these rocks, scientists continue to learn about the oceans, seas and coastlines that shaped the Permian world and supported its remarkable diversity of marine life over millions of years. During the Permian period, plant life covered large parts of the land and played an important role in shaping the environment. Plants provided food for many animals, helped form rich soils, and affected the amount of oxygen and carbon dioxide in the atmosphere. Forests stretched across many regions, although their appearance depended greatly on climate, rainfall, temperature, and the type of land where they grew. The world of the Permian was very different from the world today, and the plants that lived during this time reflected those differences. The land during the Permian was joined together into one enormous supercontinent called Pangaea. This huge landmass stretched across many climate zones, from areas close to the equator to regions much nearer the poles. Because of this, plant life was not the same everywhere. Some places were warm and wet, while others were dry and hot. There were also cool regions and places that experienced long seasonal changes. Each environment supported different kinds of plants, creating a wide variety of forests, woodlands, and open landscapes. Many of the forests that had covered Earth during the earlier Carboniferous period changed greatly by the beginning of the Permian. Earlier forests had been filled with giant club mosses, horsetails, and tree ferns, growing in large swampy areas. As the climate became drier across many regions, these wet forests slowly became smaller. Plants that depended on standing water found it harder to survive. New groups of plants that could better handle dry conditions spread into these changing landscapes. One of the most successful groups of Permian plants was the seed fern. Despite their name, seed ferns were not true ferns. Their leaves often looked like fern leaves, but instead of reproducing with spores, they produced seeds. Seeds gave these plants an important advantage because they protected the young plant inside a tough outer covering. This protection allowed this seed to survive dry weather until conditions became suitable for growth. Seed ferns became common across many parts of the supercontinent and formed an important part of many forests. Seed ferns varied greatly in size and appearance. Some were small plants growing close to the ground, while others developed into large trees with thick trunks and broad crowns. Their leaves came in many shapes, from long and narrow to wide and deeply divided. Their roots spread through the soil, helping them collect water and minerals needed for growth. Their seeds developed on special structures instead of inside flowers, since flowering plants had not yet appeared. Another important group of Permian plants was the conifers. These early relatives of modern pine trees became especially successful as dry climates spread. Conifers had several features that helped them survive where water was limited. Many had narrow leaves covered by a thick outer layer that reduced water loss. Some leaves were needle-like, while others were shaped like scales pressed against the branches. These leaves remained on the tree for long periods, allowing the plants to continue growing without producing entirely new leaves every season. The trunks of conifers contained strong wood that supported tall growth. Their bark protected them from damage and helped reduce the loss of moisture. Deep roots reached underground water, allowing many conifers to survive periods with little rainfall. Their seeds developed inside cones rather than fruits. Male cones released pollen into the air, while female cones held the seeds after fertilization. Wind carried the pollen from one tree to another, allowing reproduction even when trees stood far apart. The forests formed by early conifers often looked different from the swamp forests of earlier times. Instead of standing in waterlogged ground, many grew on dry hills, rocky slopes, river valleys, and broad plains. Their branches reached toward the sunlight and their roots helped hold the soil together. Fallen needles and branches slowly broke down, adding organic material to the ground. Another group of plants that remained important during the Permian included true ferns. Although many wet environments disappeared, ferns continued to grow wherever enough moisture remained. Riverbanks, lakesides, floodplains, and shaded valleys provided suitable places for them. Ferns reproduced by releasing tiny spores instead of seeds. These spores spread through the air and settled in damp places where new plants could develop. Tree ferns also survived in some regions. These plants had tall trunks, topped by large spreading leaves called fronds. Their appearance gave forests a rich covering of green leaves. Smaller plants often grew beneath them, creating several layers of vegetation. Animals found shelter among their trunks, roots, and fallen leaves. Horsetails continued to exist during the Permian as well. These plants had hollow stems divided into joints. Their leaves were usually small and arranged around each joint. Some species reached impressive heights, although many were smaller than their earlier relatives from the Carboniferous. Horsetails preferred moist ground and commonly grew near streams and wetlands. Club mosses, which had once dominated large swamp forests, became much less important during the Permian. Some smaller species survived in suitable habitats, but the giant tree-like forms became rare or disappeared from many places. Their decline reflected the widespread drying of the climate that affected much of the supercontinent. Another important plant group during the Permian was the ginkgophytes. These ancient relatives of the modern ginkgo tree developed broad fan-shaped leaves with veins spreading outward from the base. Their leaves captured sunlight efficiently, allowing them to produce food through photosynthesis. Ginkgophytes produced seeds rather than spores, making them well suited for changing climates. Although not as common as some other groups, they became established in several regions. The chordates were another group of seed-producing trees that had appeared earlier and continued into parts of the Permian. These trees often had long, strap-shaped leaves and tall trunks. Some species grew in wetter places, while others adapted to somewhat drier conditions. Their seeds and pollen allowed them to reproduce successfully across different environments. In the southern part of Pangaea, a very important group of plants belonged to the genus Glossopteris. These plants formed large forests across lands that are now part of South America, Africa, India, Australia, and Antarctica. Their leaves were shaped somewhat like tongues, with a network of veins running through them. Glossopteris became one of the defining plants of southern Permian ecosystems. The forests of Glossopteris played a major role in supporting animal life. Herbivorous reptiles fed on their leaves and young shoots. Fallen leaves formed thick layers on the forest floor, providing food for insects, fungi, and tiny animals. Dead wood became homes for many small creatures, while roots helped stabilize the soil. The discovery of Glossopteris fossils on several southern continents later became important evidence supporting the idea that these lands had once been connected. Scientists found nearly identical fossil leaves separated today by vast oceans. This distribution showed that the continents had once formed part of the same landmass during the Permian. Plant reproduction during the Permian showed increasing reliance on seeds. Seeds offered important protection for developing young plants. The outer covering protected the embryo from drying out, cold weather, and physical damage. Many seeds remained inactive until enough water became available for growth. This ability greatly increased the chances of survival in regions with changing rainfall. Pollen also became increasingly important. Unlike spores that often depended on water for successful reproduction, pollen could travel through the air. Wind carried enormous amounts of pollen across forests and open landscapes. Some grains landed on female reproductive structures of the same species, leading to fertilization and seed development. The climate strongly influenced where different forests grew. Near the equator, warmer temperatures supported rich plant communities where enough rainfall occurred. River systems supplied water that allowed forests to remain green for much of the year. Seasonal flooding spread nutrients across the land, helping plants grow. In regions farther from the equator, rainfall often became less reliable. Long dry seasons limited the growth of water-dependent plants. Forests became more open, with greater distances between trees. Shrubs and smaller seed plants filled many spaces that earlier might have supported dense vegetation. Some parts of the Permian world experienced desert conditions. Plant life in these areas remained sparse. Only species able to survive long periods without rain could grow successfully. Deep root systems searched for underground moisture. Thick leaves reduced water loss. Tough outer coverings protected stems from drying. Mountain regions created additional habitats for plants. Higher elevations often received more rainfall and cooler temperatures. Forests growing on mountain slopes differed from those on nearby plains. Valleys collected water flowing from higher ground, supporting richer plant communities than surrounding dry areas. Along rivers, plant life flourished because water remained available even during dry seasons. Riverbanks supported dense growth of ferns, seed ferns, horsetails, and young trees. Floods sometimes buried plants beneath layers of mud and sand. Over millions of years, these buried remains became fossils that provide valuable information today. Lakes also supported rich vegetation. Plants growing around lake shores helped reduce erosion by holding soil in place with their roots. Leaves falling into lakes settled on the bottom, sometimes becoming buried before they completely decayed. These preserved remains now help scientists understand ancient ecosystems. The soils of the Permian varied greatly from place to place. Rich soils formed where large amounts of plant material decomposed. Bacteria, fungi, and small animals broke down dead leaves, branches, and roots into simpler substances. These nutrients returned to the soil, where living plants absorbed them again through their roots. Fungi played a very important role in Permian forests. They broke down dead wood and fallen leaves that otherwise would have accumulated in thick layers. Some fungi formed close relationships with plant roots. These partnerships helped plants absorb water and minerals more efficiently, while giving fungi sugars produced during photosynthesis. Bacteria also contributed to healthy forest ecosystems. They decomposed organic matter and recycled nutrients through the soil. Some bacteria interacted with plant roots in ways that improved soil fertility. These microscopic organisms remained invisible to the animals living around them, yet they performed essential work every day. Insects were abundant in many Permian forests. Different species fed on leaves, stems, seeds, spores, and wood. Some chewed holes through leaves while others bored into trunks. Their feeding sometimes damaged plants, but forests continued growing because healthy plants usually replaced lost leaves. Some insects laid eggs inside plant tissues, protecting their young during early development. Others depended on dead wood or fallen leaves for food. The variety of plant life supported many kinds of insects, each occupying different parts of the forest. Large reptiles also depended on Permian plants. Herbivorous species ate leaves, stems, seeds, and other plant parts. Their feeding affected plant growth by removing vegetation from certain areas. Some animals spread seeds as they moved across the landscape. Others disturbed the soil while searching for food. creating places where new plants could grow. Carnivorous reptiles relied indirectly on forests because the herbivores they hunted depended on plant life. Without healthy forests and plant communities, the larger food chains could not survive. Plants formed the foundation of nearly every land ecosystem during the Permian. Photosynthesis remained one of the most important biological processes throughout the Permian. Plants used sunlight to combine water and carbon dioxide into sugars that provided energy for growth. Oxygen was released into the atmosphere during this process. Every leaf contributed in a small way to maintaining the balance of gases needed by living organisms. The amount of sunlight reaching different forests depended on latitude, seasons, cloud cover, and the arrangement of leaves within the forest. Tall trees often received the greatest amount of sunlight, while smaller plants growing beneath them adapted to shadier conditions. Different leaf shapes allowed plants to capture available light efficiently. Growth rings developed inside many Permian trees. Each ring recorded changing conditions during a year of growth. Wide rings usually formed when conditions favored rapid growth, while narrow rings reflected slower growth. Fossil wood containing these rings now helps scientists study ancient climates and seasonal patterns. Forest fires probably occurred naturally during parts of the Permian. Lightning could ignite dry vegetation during storms. Fires cleared dead plant material and opened space for new growth. Some plants may have possessed features that helped them survive occasional fires, although evidence remains limited. Wind shaped many Permian forests by carrying pollen, dispersing seeds, and sometimes breaking branches during powerful storms. Trees growing in exposed areas often developed strong trunks capable of resisting repeated winds. Fallen trees created openings where sunlight reached the forest floor, allowing young plants to grow. Seasonal changes influenced plant growth throughout much of the Permian. During wetter seasons, many plants produced new leaves, seeds, and reproductive structures. During drier periods, growth slowed as water became less available. Some plants shed leaves to reduce water loss until favorable conditions returned. The southern regions of Pangaea experienced cooler climates in some areas because they lay closer to the South Pole. Earlier glaciers had shaped much of this landscape. As climates gradually changed, forests spread across land that had previously been covered by ice. Glossopteris forests became especially successful in these southern environments. Antarctica during the Permian supported forests unlike the frozen landscape found there today. The continent occupied a different position than it does now, and although winters included long periods of darkness, forests still grew successfully. Fossil wood, leaves, roots, and seeds discovered there reveal the presence of thriving plant communities. Plant fossils provide much of what scientists know about Permian forests. Fossil leaves preserve vein patterns, shapes, and sizes. Fossil wood reveals internal structures and growth rings. Fossil pollen grains survive in rocks because of their durable outer walls. Fossil seeds, cones, and roots provide additional information about ancient plant reproduction and growth. Some fossils formed when volcanic ash quickly buried forests. The ash-protected plant remains from rapid decay. Minerals slowly replaced the original tissues, preserving fine details that remain visible today. Other fossils formed as impressions pressed into soft mud that later hardened into rock. Coal deposits formed mainly from earlier Carboniferous swamp forests, but some coal continued forming during parts of the Permian where wet environments remained. Thick accumulations of plant material buried beneath sediments slowly changed under heat and pressure over millions of years. Plant diversity during the Permian reflected millions of years of evolution. New groups expanded while older groups declined. Environmental changes created opportunities for plants with features suited to dry climates. Seed-producing plants became increasingly important because they reproduced successfully across a wider range of conditions. The structure of Permian forests varied widely. Some forests contained towering trees, forming a closed canopy that shaded the ground below. Others consisted of scattered trees, separated by open spaces filled with shrubs, seed ferns, and smaller vegetation. Wetlands supported dense plant growth, while dry uplands contained thinner forests. The forest floor contained fallen branches, leaves, cones, seeds, spores, fungi, insects, and countless tiny organisms. Decomposition constantly recycled nutrients. Young plants sprouted wherever sunlight reached the ground. Roots spread beneath the surface, competing for water and minerals. Tree trunks provided homes for insects and other small animals. Rough bark protected living tissues beneath, while creating small spaces where tiny organisms could live. Dead standing trees remained useful parts of the forest long after they stopped growing. Roots anchored trees against wind and helped absorb water from deep underground. Fine root hairs increased the surface available for taking in moisture and dissolved minerals. Root systems also helped prevent soil from washing away during heavy rains. Plant chemistry also influenced Permian ecosystems. Leaves contained different substances that affected which animals could eat them. Some plants produced chemicals that discouraged feeding by insects or reptiles. Others developed thick tissues that made leaves harder to chew. The color of Permian forests changed with the seasons and with local conditions. Fresh young leaves appeared bright green because of chlorophyll. Older leaves gradually aged before falling to the ground. Dry regions often supported plants with smaller leaves that reduced water loss. Many plants lived for decades or even centuries. Large trees slowly increased in height and width each year. Smaller plants completed their life cycles more quickly, producing seeds or spores before dying. This mixture of long-lived and short-lived plants created stable forest communities capable of recovering after disturbances. Water remained one of the greatest factors controlling plant distribution. Areas with dependable rainfall supported thicker forests and greater diversity. Places receiving little rainfall developed more open vegetation dominated by drought-resistant species. River systems acted as lifelines across otherwise dry landscapes. As the Permian progressed, climates in many regions became even drier. Seed plants continued spreading while many spore-producing plants became restricted to wetter habitats. Conifers expanded into environments unsuitable for earlier swamp vegetation. Their success marked an important stage in the history of forests. The rise and diversity of synapsids, often called mammal-like reptiles, is one of the most important parts of the history of life on Earth. These animals appeared long before the first true mammals. They lived during a time when the continents were still moving toward each other and later became joined into the great supercontinent known as Pangaea. Synapsids were among the most successful land animals of their time. They spread across many different environments and slowly developed many features that later became common in mammals. Even though they are often called mammal-like reptiles, scientists today understand that synapsids were not true reptiles. They belong to their own separate branch of vertebrate animals. Mammals later evolved from this branch after many millions of years of change. The first synapsids appeared during the late part of the Carboniferous period, more than 300 million years ago. At that time, the world was covered in many forests filled with giant club mosses, ferns, horsetails, and seed plants. Warm wetlands stretched across large areas, and many rivers and swamps supported many kinds of life. Early synapsids shared this world with amphibians and many other early land animals. They were among the first vertebrates to become fully successful on land because they reproduced using amniotic eggs. These eggs had protective membranes that allowed young animals to develop without needing to remain in water. This important feature made it possible for synapsids to spread into drier places where amphibians could not easily survive. The word synapsid comes from the structure of the skull. These animals had a single opening behind each eye socket. This opening allowed space for stronger jaw muscles. Larger jaw muscles helped them bite with greater force and control. This simple change in the skull became one of the defining features of the entire synapsid group. It also gave later members of the group the ability to chew food more effectively than many other early land animals. The earliest synapsids were known as pelycosaurs. They were the first large land vertebrates to become widespread across many regions. Although they are often shown as reptile-like animals in books and museums, they belong to the synapsid branch. Their bodies usually had long tails, sturdy legs, broad feet, and long heads filled with many teeth. Different kinds of teeth were already beginning to appear in some species. This was an early step toward the specialized teeth that mammals later developed. Many pelycosaurs were plant eaters. Others were meat eaters. Some were able to eat almost any available food. This wide range of feeding habits helped synapsids occupy many different habitats. Plant-eating species fed on ferns, seed ferns, early conifers, and other plants that grew during the late Carboniferous and Permian periods. Meat-eating species hunted smaller animals or fed on dead bodies left behind by other predators. One of the best-known early synapsids was Dimetrodon. This animal lived during the early part of the Permian period. It had a large body, a long tail, strong jaws, and many sharp teeth. The feature that made it famous was the large sail rising from its back. This sail was supported by long bones extending upward from the backbone. Scientists have suggested several possible uses for this sail. It may have helped control body temperature by collecting warmth from sunlight or releasing excess heat. It may also have been used to attract mates or to warn rivals. Different ideas continue to be studied because soft tissues do not survive well in fossils. Dimetrodon was one of the largest predators of its time. Its long teeth could grip struggling prey, while its powerful jaw muscles produced a strong bite. It hunted many smaller animals living in rivers, floodplains, forests, and dry lands. Fossils show that Dimetrodon lived across parts of what are now North America and Europe, showing that these regions were once connected as part of Pangaea. Another famous sail-backed synapsid was Edaphosaurus. Unlike Dimetrodon, Edaphosaurus mainly ate plants. It had a shorter head, smaller teeth suited for crushing vegetation, and a large body supported by strong limbs. Its sail looked different because it contained many short side branches growing from the long supporting bones. Scientists continue to study whether this sail served similar purposes to that of Dimetrodon or had additional functions related to display. Many other pelycosaurs did not have sails. They came in many sizes and shapes. Some remained small enough to hide beneath thick vegetation. Others became large animals that wandered across open ground. Some species had stronger limbs for walking long distances. Others stayed close to rivers and lakes where food and water remained available. As the Permian period continued, another important group of synapsids appeared. These animals were called therapsids. They gradually replaced many earlier pelycosaurs and became the dominant land vertebrates across large parts of the world. Therapsids showed many important changes that moved the synapsid family closer to true mammals. The skulls of therapsids became shorter and deeper. Their jaws became stronger, and the muscles used for chewing became larger. Their teeth also became more specialized. Instead of having many teeth that looked almost the same, different teeth developed different jobs. Sharp front teeth could grab food. Long pointed canine teeth could tear flesh or defend against enemies. Broader teeth farther back in the mouth could crush or grind food. This arrangement improved feeding and digestion. The legs of therapsids slowly changed position. Earlier synapsids usually had limbs that spread outward from the sides of the body. Many therapsids developed legs that stood more directly beneath the body. This made walking more efficient and reduced the amount of energy needed for movement. It also allowed many species to travel longer distances while searching for food, water, or mates. The backbone also became stronger in many therapsids. Their bodies could better support their weight while moving across land. The neck became more flexible in some species, allowing better control of the head while feeding or watching for danger. Some therapsids became powerful meat-eaters. Others became successful plant-eaters. There were also species that probably ate insects or mixed diets, depending on what food was available. This wide variety allowed therapsids to spread into forests, open plains, river valleys, floodplains, and dry interior regions of Pangaea. One important group of therapsids was the Dinosaurs. Many members of this group grew into very large animals. Some had thick skull bones that may have been used during fights between members of the same species. Others developed heavy bodies supported by strong legs. Plant-eating Dinosaurs spent much of their time feeding on low-growing vegetation. Meat-eating members hunted other large animals. Another successful group was the Anomodonts. The best-known members of this group were the Dicynodonts. Most Dicynodonts had beak-like mouths instead of many front teeth. Some species had only a pair of long tusks growing from the upper jaw. Their beaks allowed them to cut through tough plants. Strong muscles inside the mouth helped process food before swallowing. Dicynodonts became some of the most successful plant-eating animals of the Permian and continued surviving into the following Triassic period. The Gorgonopsians formed another important branch of therapsids. These animals were among the leading predators during the late Permian. They had long heads, powerful jaws, and large saber-shaped canine teeth. Their bodies combined strength with improved movement. They hunted many kinds of plant-eating animals across the Great Plains and forests of Pangaea. Another important group was the Therocephalians. These animals showed several advanced features in their skulls and jaws. Some species remained small hunters that searched for insects, reptiles, amphibians, and small synapsids. Others reached larger sizes. Their fossils suggest increasing changes toward the jaw structure later seen in mammals. The cynodonts became one of the most important branches of therapsids, because true mammals later evolved from this group. Cynodonts developed many features that are familiar today. Their teeth became even more specialized. Their jaws allowed stronger chewing. Their faces became shorter. The bones inside the lower jaw slowly changed through evolution. Over time, some of these bones became part of the middle ear in mammals, improving hearing. Scientists study fossil skulls very carefully because they preserve evidence of these changes. Early synapsids had lower jaws made from several bones. As evolution continued, one bone became larger while the others became smaller. Eventually, mammals developed a lower jaw made mainly from a single bone, while the smaller bones became tiny hearing bones inside the ear. many cynodonts probably had whiskers. Tiny openings in fossil skulls suggest that nerves once passed through these areas to support sensitive facial hairs. Whiskers help detect objects, movement, and changes in the surrounding environment. If these early animals possessed whiskers, they may have been active during the evening or night when eyesight alone was less useful. Scientists also believe that many later therapsids developed hair or fur. Hair rarely becomes fossilized, so direct evidence is uncommon. However, several lines of evidence suggest its presence. Hair helps keep body heat inside the body. This is especially useful for animals with high activity levels and warm body temperatures. Many researchers believe that some later synapsids gradually developed warm-blooded bodies. Instead of depending mainly on outside temperatures, they produced much of their own body heat. This allowed them to remain active under a wider range of weather conditions. Growing evidence from bone structure, blood vessel patterns, and other fossil features supports this idea, although the exact timing remains under study. Breathing also changed during synapsid evolution. Earlier animals may have breathed less efficiently because of the position of their ribs and body muscles. Later, therapsids probably developed better breathing systems that allowed more oxygen to enter the lungs during movement. Increased oxygen supply supported higher activity levels and greater endurance. The development of a secondary palate was another important change. This structure formed a bony roof inside the mouth. It separated the air passage from the mouth used for chewing. Animals with this feature could breathe while holding food inside the mouth. This made feeding more efficient and allowed longer chewing before swallowing. Bone growth changed as synapsids evolved. The bones of many therapsids show faster growth than those of many earlier land vertebrates. Faster growth allowed young animals to reach larger sizes sooner. This may have reduced the time during which young animals remained vulnerable to predators. Different synapsids occupied many ecological roles during the Permian. Large predators controlled populations of plant eaters. Medium-sized hunters fed on smaller animals. Plant eaters consumed leaves, stems, seeds, and other plant material. Smaller insect eaters reduced insect numbers. Scavengers cleaned dead animals from the environment. The climate of the Permian influenced synapsid evolution. Early in the period, many regions remained warm with seasonal rainfall. As time passed, much of the interior of Pangaea became drier. Deserts expanded across large areas. Rivers became more seasonal in some regions. Plants changed as conditions became less suitable for wetland forests. Synapsids adapted to these environmental changes in different ways. Some species developed stronger limbs for traveling long distances between food sources. Others became better at conserving water. Plant eaters shifted toward feeding on tougher plants that survived in dry conditions. Meat eaters followed the movements of their prey across changing landscapes. Fossils of synapsids have been found on several continents. Important discoveries have come from what are now South Africa, Russia, China, Brazil, North America, and Europe. During the Permian, these lands were joined together within Pangaea, allowing many animals to spread across wide regions without crossing oceans. South Africa has provided one of the richest collections of therapsid fossils in the world. Layers of rock preserve complete skeletons, footprints, burrows, and other evidence of ancient life. Scientists have used these fossils to understand growth, movement, feeding habits, and evolution. Some synapsids probably dug burrows underground. Burrows provided protection from heat, cold, predators, and dry weather. Fossil burrows containing skeletons have been discovered in several places. Some burrows appear large enough for adults and young to live together for periods of time. There is also evidence that some therapsids cared for their young after birth or hatching. Although direct proof is limited, fossils showing adults and young preserved together suggest that family groups may have existed in certain species. Extended care of young later became an important characteristic of mammals. Brain size gradually increased in several branches of therapsids. Fossil skulls allow scientists to study the space once occupied by the brain. Areas linked with smell became especially well developed. Strong senses of smell helped locate food, detect predators, identify mates, and recognize territories. Eyes also changed in some groups. Larger eye sockets suggest improved vision. Combined with better hearing and smell, these sensory improvements allowed more effective hunting and survival. The skin of synapsids is not well known because soft tissues rarely survive. Some may have had scales covering much of the body. Others may have developed patches of hair while still retaining areas of bare skin. As evolution continued, hair probably became more widespread among later members, leading toward mammals. Many synapsids laid eggs early in their history, although direct fossil evidence is rare. Later stages leading toward mammals eventually evolved live birth in some branches. Exactly when this happened remains uncertain because reproductive organs almost never fossilize. The Permian ended with the largest known mass extinction in Earth's history. Huge volcanic eruptions, changing climates, reduced oxygen levels, ocean changes, and many other environmental disturbances caused widespread destruction of life. Many groups of plants and animals disappeared forever. The extinction greatly affected synapsids. Numerous families vanished during this event. Many large predators disappeared. Several plant-eating groups also became extinct. Only a limited number of therapsid branches survived into the Triassic period. Among the survivors were certain cynodonts and dicynodonts. These remaining animals entered a world that had changed greatly after the extinction. Forests had been reduced in many places. Food chains had been disrupted. Ecosystems slowly began recovering over long periods. The surviving cynodonts continued evolving throughout the Triassic. Their jaws became even more efficient for chewing. Their teeth became increasingly specialized. Their posture became more upright. Hair likely became more widespread. Warm-blooded metabolism probably became more fully developed. Over many millions of years, these gradual changes eventually produced the earliest true mammals. These small animals inherited many features from their synapsid ancestors, including differentiated teeth, improved hearing, efficient chewing, advanced breathing, body hair, and greater parental care. Modern mammals, including humans, are descendants of these ancient synapsids. Every living mammal carries anatomical features that first began appearing during the long history of synapsid evolution. The single opening behind the eye in the skull, specialized teeth, complex jaw muscles, and several ear bones all trace their origins to these early ancestors. The fossil record continues to expand every year as new discoveries are made in different parts of the world. Improved imaging methods allow scientists to examine fossil skulls without damaging them. Microscopic studies of bone tissue reveal growth rates, age, disease, injuries, and patterns of blood supply. Computer models help researchers study movement, bite force, and muscle attachment. New discoveries sometimes change earlier ideas about relationships among different synapsid groups. Fossils showing intermediate stages provide valuable evidence for understanding how major evolutionary changes occurred gradually over long periods. Each newly discovered skeleton adds another piece to the history of life. The diversity of synapsids during the Permian included animals of many sizes, shapes, diets, and lifestyles. Some remained only a short distance above the ground while moving. Others stood higher on stronger limbs. Some possessed long tails while others had shorter ones. Heads ranged from narrow to broad. Teeth varied according to feeding habits. Body size ranged from small insect hunters to large plant eaters and powerful predators. Growth patterns also differed among species. Some matured quickly and lived shorter lives. Others grew for longer periods before reaching full size. Bone studies show seasonal growth in several species, reflecting changes in climate and food availability during different times of the year. Disease and injury affected synapsids just as they affect animals today. Fossil bones sometimes preserve healed fractures, infections, bite marks, damaged joints, and worn teeth. These fossils show that many individuals survived serious injuries and continued living long afterward. Interactions between predators and prey shaped the evolution of many synapsids. Faster movement, stronger jaws, thicker bones, defensive tusks, larger body size, and improved senses all developed under natural selection across many generations. Plant eaters and meat eaters influenced each other's evolution as they adapted to changing environments and changing food supplies. Synapsids also interacted with many other forms of life. They shared their habitats with amphibians, early reptiles, insects, spiders, scorpions, fish, living in nearby rivers and lakes, and many kinds of plants. These living communities formed complex ecosystems in which every species depended directly or indirectly upon many others for survival. Seasonal rainfall influenced food supplies across much of the Permian world. During wetter times, plants grew more abundantly. During dry seasons, food became harder to find in some areas. Synapsids responded by moving to better habitats, feeding on different plants, or hunting different prey depending on local conditions. The success of synapsids throughout much of the Permian resulted from their ability to adapt to changing climates, changing landscapes, and changing food sources. Different branches evolved unique body structures suited to their particular ways of life. Some specialized in grazing on low vegetation. Others became active hunters. Some dug underground shelters. Others traveled across open plains. Each generation inherited small changes from the one before it. Over very long periods, these small changes accumulated into major differences. New species appeared while older species disappeared. Entire branches expanded into many forms, while others ended through extinction. This long process produced the remarkable diversity recorded in Permian rocks across the world. Scientists continue studying footprints left by synapsids because tracks provide valuable information that skeletons alone cannot reveal. Footprints show walking speed, direction of movement, group behavior, and the condition of ancient ground surfaces. Some trackways indicate steady walking, while others suggest running. In a few places, several trackways preserved together hint that groups of animals moved across the landscape at the same time. Buried skeletons sometimes preserve animals in resting positions, curled positions, or inside underground shelters. These discoveries provide clues about daily behavior and survival strategies. Combined with studies of bones, teeth, footprints, burrows, and surrounding rocks, they allow scientists to build an increasingly detailed understanding of synapsid life during the Permian Period. The Permian to Triassic extinction event was the largest known mass extinction in the long history of Earth. It happened near the end of the Permian Period and marked the beginning of the Triassic Period. This event changed life across the entire planet. Many groups of living things that had existed for millions of years disappeared forever. Plants, animals, fungi, and tiny forms of life were all affected in different ways. The event took place about 252 million years ago. Scientists continue to study this period because it provides important information about how life reacts to severe environmental change. Before this extinction began, Earth was very different from the world that exists today. Most of the land was joined together into one giant supercontinent called Pangaea. A huge ocean known as Pangaea surrounded this landmass. Another large sea called the Paleotethys stretched into parts of the supercontinent. Large deserts covered many inland regions because moisture from the oceans could not easily reach the center of the vast landmass. Forests grew in wetter areas, while many rivers, lakes and wetlands supported different forms of life. The oceans were filled with many kinds of living creatures. Coral reefs supported rich communities of animals. Brachiopods covered the sea floor in many places. Crinoids, sea lilies, ammonoids, trilobites, bryozoans, sponges and many shellfish lived in shallow and deep waters. Fish of many kinds swam through rivers and seas. Sharks and other ancient fish hunted smaller animals. Tiny floating organisms drifted through the water and formed the base of the marine food chain. On land, many groups of plants covered different environments. Large forests contained seed ferns, conifers, ginkgophytes, and other early seed plants. Mosses and small plants grew close to the ground in damp places. Insects were very successful and filled almost every available habitat. Many different kinds of reptiles and synapsids lived across the continents. Synapsids included animals that shared important features with later mammals. Some were large plant eaters, while others hunted smaller animals. Life during the late Permian had become highly diverse after many millions of years of evolution. Different regions supported their own collections of plants and animals. Many species had become well adapted to local climates and environments. Although life had survived earlier extinction events, the conditions at the end of the Permian created problems that became far greater than anything many living organisms had experienced before. Scientists believed that no single small event caused the extinction. Instead, many environmental changes happened close together. Some changes may have begun before others. Some continued for a very long time. These changes affected the atmosphere, the oceans, the climate, and the land. As each problem developed, living things faced increasing difficulty in finding food, reproducing, and surviving. The strongest evidence points to enormous volcanic eruptions in an area that is now part of northern Asia. These eruptions created one of the largest volcanic regions ever formed on Earth. Today this region is known as the Siberian Traps. The eruptions covered huge areas with layers of lava. They continued over a very long period instead of ending after a single eruption. Large amounts of molten rock reach the surface again and again. When volcanoes erupt, they release gases into the atmosphere. During the formation of the Siberian Traps, the amount of gas released was extremely large. Carbon dioxide entered the atmosphere in huge quantities. Water vapor, sulfur gases, and other volcanic gases also escaped from deep inside Earth. These gases changed the chemistry of the atmosphere and affected the climate around the world. Carbon dioxide is a greenhouse gas. When its amount increases, more heat remains trapped in the atmosphere. Over time, global temperatures began to rise. This warming did not happen everywhere in exactly the same way, but evidence from rocks and fossils shows that much of the planet became much hotter than before. Higher temperatures created difficult conditions for many plants and animals that depended on cooler environments. The warming affected both land and sea. On land, hotter conditions increased evaporation. Rivers and lakes became smaller in some places. Dry regions expanded. Plants that depended on regular rainfall struggled to survive. As forests declined, many animals lost their food and shelter. Soil also became more vulnerable to erosion when plant cover decreased. The oceans absorbed much of the extra heat from the atmosphere. As seawater became warmer, it held less dissolved oxygen. Marine animals depend on oxygen in seawater just as land animals depend on oxygen in the air. Lower oxygen levels created stressful conditions for fish, shellfish, and many other sea creatures. Some parts of the oceans became so low in oxygen that many animals could no longer survive there. Scientists call these low oxygen conditions ocean anoxia. During the extinction event, anoxia spread through large areas of the world's oceans. Deep waters became especially poor in oxygen, but shallow waters were also affected in many places. Animals that could not move into better conditions died in great numbers. Species that depended on well-oxygenated water became especially vulnerable. Another serious problem was ocean acidification. As more carbon dioxide entered the atmosphere, much of it dissolved into seawater. This changed the chemistry of the oceans. More acidic water made it difficult for many marine animals to build shells and skeletons made from calcium carbonate. Corals, brachiopods, some plankton, and many shell-forming organisms faced increasing difficulty growing and reproducing. Coral reefs suffered severe damage during this time. Reef-building organisms require stable environmental conditions. Rising temperatures, changing ocean chemistry, and falling oxygen levels all reduce their ability to survive. Many reef communities disappeared completely. Since reefs provided homes for countless other organisms, their destruction affected many different species at the same time. The volcanic eruptions also released sulfur dioxide into the atmosphere. Sulfur gases reacted with water vapor to produce acidic rainfall. Acid rain damaged leaves, weakened forests, changed the chemistry of lakes and rivers, and affected soils. Plants growing in already difficult conditions became even more stressed. Reduced plant growth meant less food for plant-eating animals. Some scientists believed that the lava flowed across thick layers of coal, oil, natural gas, and organic-rich rocks buried underground. The intense heat from the magma caused these materials to burn or break down. This process released even more carbon dioxide and methane into the atmosphere. Methane is another greenhouse gas that can trap heat very effectively. Additional methane would have increased global warming even further. Frozen methane stored beneath the seafloor may also have been released as ocean temperatures increased. Methane can remain trapped inside ice-like structures under cold conditions. When the temperatures rise, these structures become unstable and release gas into the water and atmosphere. Scientists continue to study how much methane entered the atmosphere from this source, but it may have added to the warming that was already taking place. As temperatures continued to rise, weather patterns changed across the planet. Some regions experienced longer droughts. Other areas may have received periods of heavy rainfall followed by dry conditions. Seasonal patterns became less stable. Plants that depended on regular growing seasons found it harder to survive. Changes in rainfall also affected rivers and freshwater habitats. Many rivers carried larger amounts of soil into the oceans because forests and other plants no longer protected the land. Sediment spread across shallow seas and changed marine environments. Extra nutrients washed into coastal waters. These nutrients encouraged rapid growth of microorganisms. When these organisms died and decomposed, they used even more oxygen from the water, making low oxygen conditions even worse. The decline in oxygen was not limited to the oceans. Some studies suggest that oxygen levels in the atmosphere also fell during parts of this period. Animals living on land may have found breathing more difficult, especially large active species. Lower oxygen could also have affected the growth and development of many organisms. The food chains that supported life began to break apart. Plants weakened or disappeared in many areas. Plant-eating animals had less food available. Meat-eating animals then found fewer prey animals to hunt. Each loss affected many other species, connected through feeding relationships. Even small changes at the bottom of the food chain spread through entire ecosystems. Tiny organisms living in the oceans also experienced severe losses. Many kinds of plankton disappeared. Since plankton formed the foundation of marine food chains, larger animals that depended on them also declined. Fish populations became smaller in many places. Predators lost important food sources. Entire marine ecosystems became much less diverse. Microorganisms played an important role during the extinction event. Some bacteria can survive in oxygen-poor environments. As oxygen levels dropped, these bacteria spread into larger areas. Certain kinds produced hydrogen sulfide gas. This gas is poisonous to many forms of life. If large amounts reached surface waters or escaped into the atmosphere, they could have created even more dangerous conditions. Hydrogen sulfide can damage living cells and interfere with normal biological processes. Plants, animals, and many microorganisms cannot tolerate high amounts of this gas. Scientists have found evidence suggesting that hydrogen sulfide may have become widespread in some oceans during the extinction event. This would have increased the stress already caused by warming, acidification, and low oxygen. The extinction did not happen everywhere at exactly the same moment. Different groups disappeared at different times. Some regions experienced severe losses earlier than others. Environmental changes spread across the planet over thousands of years. Each new change added pressure to ecosystems that were already weakened. Many species that had survived previous environmental changes could not survive this combination of problems. Adaptation usually requires long periods of stable conditions that allow natural selection to produce new traits. During the Permian to Triassic extinction event, changes happened so quickly and affected so many parts of the environment that many organisms had little chance to adapt successfully. Marine life experienced especially severe losses. Scientists estimate that around 90% of marine species disappeared during the extinction event. Entire families and larger groups vanished forever. Trilobites, which had lived in the oceans for hundreds of millions of years, became completely extinct. Many brachiopods disappeared. Reef-building organisms suffered enormous losses. Crinoids, ammonoids, and many other marine groups declined sharply. Fish also experienced major losses, although some groups survived and later became successful again. Sharks lost many species. Primitive bony fish populations were greatly reduced. Marine reptiles had not yet become important parts of ocean ecosystems. So the seas after the extinction looked very different from those that existed later in the Triassic. Life on land also suffered greatly. Scientists estimate that around 70% of land vertebrate species became extinct. Many synapsids disappeared completely. Several important reptile groups also vanished. Only a limited number of species survived to give rise to later populations. Large plant-eating animals faced severe food shortages as forests and other vegetation declined. Meat-eating animals then struggled because prey became scarce. Animals that required specialized diets were especially vulnerable because they could not easily switch to different food sources. Plants experienced large losses, although complete extinction among plant groups was generally lower than among animals. Even so, forests disappeared from many regions. Fossil evidence shows periods when dead plant material accumulated without signs of rapid forest recovery. Some landscapes remained open and sparsely vegetated for long periods after the extinction. Spores produced by fungi became unusually common in some rock layers formed during this time. Scientists believe this reflects the widespread death of forests and plants. Fungi feed on dead organic matter, so large amounts of dead vegetation would have provided abundant food for them. Similar patterns can sometimes be seen after modern forest disasters. Insects also experienced one of the largest extinction events in their history. Many insect families disappeared completely. This is unusual because insects often survive environmental changes better than many larger animals. The widespread collapse of forests and plant communities removed habitats and food sources that many insects depended on. Freshwater environments were affected as well. Rivers and lakes experienced changes in water temperature, oxygen levels, and water chemistry. Fish, amphibians, and freshwater invertebrates faced difficult conditions. Some freshwater groups survived better than marine organisms, but many populations still declined. Scientists study rocks formed during this period to understand what happened. Sedimentary rocks preserve evidence of changing environments. Different layers contain fossils, minerals, chemical signals, and volcanic ash. By examining these layers, researchers can estimate the order in which events occurred. Chemical elements trapped inside rocks provide valuable clues. Different forms of carbon record changes in the global carbon cycle. Oxygen isotopes preserve information about ancient temperatures. Sulfur compounds help scientists understand changes in ocean chemistry. These different kinds of evidence allow researchers to build a detailed picture of environmental change during the extinction. Volcanic ash layers can often be dated very accurately using radioactive elements found in certain minerals. These measurements have allowed scientists to estimate that the main extinction occurred over a relatively short geological interval, although the environmental disturbances before and after continued much longer. Some scientists have suggested that asteroid impacts may also have contributed to the extinction. Large impacts have caused major environmental changes at other times in Earth's history. However, evidence for an impact at the end of the Permian is much weaker than the evidence supporting massive volcanic eruptions. Most researchers currently consider volcanism to have been the primary cause. Other possible contributing factors include changes in sea level, movement of continents, changes in ocean circulation, and release of gases from deep underground. These processes may have worked together with volcanic activity instead of acting independently. Earth systems are closely connected, so a major disturbance in one system often affects many others. The arrangement of the continents also influenced environmental conditions. Because Pangaea formed one enormous landmass, many inland regions were already dry before the extinction. As temperatures increased, these dry conditions became even more severe. Water became less available in some areas, increasing stress on plants and animals. Ocean circulation changed as temperatures rose. Normally, ocean currents help move oxygen-rich water into deeper regions. During the extinction event, warming may have reduced this mixing. Deep waters remained isolated for longer periods and gradually lost oxygen. This created larger regions where only a few specialized microorganisms could survive. Many surviving species were those with broader environmental tolerance. Animals able to live in different habitats or eat different foods often had a better chance of survival. Small body size may also have helped some organisms, because smaller animals generally require less food than larger ones. Burrowing animals survived in greater numbers than many surface-dwelling species. Underground burrows protected them from some temperature extremes and provided more stable conditions. These shelters may also have helped retain moisture during long dry periods. Some plant species survived because their seeds remained protected in the soil until conditions improved. Seeds can sometimes survive difficult environmental conditions better than fully grown plants. Once temperatures and rainfall became more favorable, surviving seeds helped restore vegetation in damaged landscapes. Recovery after the extinction was very slow. Many ecosystems remained simple for millions of years. Instead of rich communities containing many species, early Triassic environments often contained only a few dominant organisms. Biodiversity increased only gradually as new species evolved and spread into empty habitats. The oceans required a long time to recover because oxygen levels remained low in many regions. Coral reefs did not immediately return. Reef ecosystems remained rare for millions of years. Marine animals slowly evolved into new forms that filled ecological roles left empty by extinct species. On land, surviving synapsids and reptiles began expanding into habitats where competitors had disappeared. Over time, reptiles known as archosaurs became increasingly successful. This group later produced crocodiles, pterosaurs, and dinosaurs. Mammal ancestors also survived through a few hardy synapsid lineages that eventually gave rise to true mammals much later. The extinction permanently changed the direction of evolution. Many ancient groups that had dominated the Permian never returned. New groups slowly appeared and diversified during the Triassic. The balance of life on Earth became different from what had existed before the extinction.